Hello. All right, we ready to code? Let's review what we did last time. So we're reading through this book, Neural Networks and Deep Learning. We haven't gotten very far yet, but we've implemented a perceptron and a sigmoid single neuron. A perceptron is a circuit, I guess you could call it, where its output is binary, either 0 or 1, depending on the product of its weights and its input, plus its bias, whether that's positive or negative. We saw that you can make you can do any computation out of perceptrons because you can simulate NAND gates. That's what this was. Then we started talking about sigmoids. Sigmoids are a continuous generalization of perceptrons. So instead of just checking if Z is positive or negative, we pipe it through this sigmoid function. And that's when Z is really big or really small, that's the same as checking if it's positive or negative, but when it's closer to 0, it's more continuous. And the reason we did this was so that if we change the inputs a little bit, or the weights or the biases a little bit, then that should only change the output a little bit instead of flipping it completely from 0 to 1. So let's keep going. The architecture of neural networks. In the next section, I'll introduce a neural network that can do a pretty good job classifying handwritten digits. In preparation for that, it helps to explain some terminology that lets us name different parts of a network. Suppose we have the network blah. As mentioned earlier, the leftmost layer in this network is called the input layer, and the neurons within the layer are called input neurons. The rightmost or output layer contains the output neurons, or, as in this case, a single output neuron. The middle layer is called a hidden layer, since the neurons in this layer are neither inputs nor outputs. The term hidden perhaps sounds a little mysterious. The first time I heard the term, I thought it must have some deep philosophical or mathematical significance. But it really means nothing more than not an input or an output. The network above has just a single hidden layer, but some networks have multiple hidden layers. For example, the following 4-layer network has 2 hidden layers. Input, hidden, hidden, output. Somewhat confusingly, and for historical reasons, such multiple layer networks are sometimes called multi-layer perceptrons, or MLPs, despite being made up of sigmoid neurons, not perceptrons. I'm not going to use the MLP terminology of this book, since I think it's confusing, but I wanted to warn you of its existence. The design of the input and output layers in a network is often straightforward. For example, suppose we're trying to determine whether a handwritten image depicts a 9 or not. A natural way to design the network is to encode the intensities of the image pixels into the input neurons. If the image is a 64 by 64 grayscale image, then we'd have 4096 equals 64 times 64 input neurons, with the intensities scaled appropriately between 0 and 1. The output layer will contain just a single neuron, with output values of less than 0.5 indicating input image is not a 9, and values greater than 0.5 indicating input image is a 9. While the design of the input and output layers of a neural network is often straightforward, there can be quite an art to the design of hidden layers. In particular, it's not possible to sum up the design process for the hidden layers with a few simple rules of thumb. Instead, neural networks researchers have developed many design heuristics for the hidden layers, which help people get the behavior they want out of their nets. For example, such heuristics can be used to help determine how to trade off the number of hidden layers against the time required to train the network. We'll meet several such design heuristics later in this book. Up to now, we've been discussing neural networks where the output from one layer is used as the input to the next layer. Such networks are called feed-forward neural networks. This means that there are no loops in the network. Information is always fed forward, never fed back. If we did have loops, we'd end up with situations where the input of the sigmoid function depended on the output. That'd be hard to make sense of, and so we don't allow such loops. However, there are other models of artificial neural networks in which feedback loops are possible. These models are called recurrent neural networks. And I think we will need recurrent neural networks in order to make an LLM. I think you need recurrence in order to do text processing, but I'm not sure. The idea in these models is to have neurons which fire for some limited duration of time before becoming quiescent. That firing can stimulate other neurons, which may fire a little while later. Also for a limited duration. That causes still more neurons to fire, and so over time we get a cascade of neurons firing. Loops don't cause problems in such a model since a neuron's output only affects its input at some later time, not instantaneously. Recurrent neural nets have been less influential than feed-forward networks, in part because the learning algorithms for recurrent nets are, at least to date, less powerful. But recurrent networks are still extremely interesting. They're much closer in spirit to how our brains work than feed-forward networks, and it's possible that recurrent networks can solve important problems which can only be solved with great difficulty by feed-forward networks. However, to limit our scope in this book, we're going to concentrate on the more widely used feed-forward networks. Okay, if recurrent nets are not widely used, then maybe I'm wrong that you need them for text processing. A simple network to classify handwritten digits. Having defined neural networks, let's return to handwriting recognition. We can split the problem of recognizing handwritten digits into two subproblems. First, we'd like a way of breaking an image containing many digits into a sequence of separate images, each containing a single digit. For example, we'd like to break the image 504192 into 6 separate images, 504192. We humans solve this segmentation problem with ease, but it's challenging for a computer program to correctly break up the image. Once the image has been segmented, the problem then needs to classify each individual digit. So for instance, we'd like our program to recognize that the first digit above, 5, is a 5. We'll focus on writing a program to solve the second problem, that is, classifying individual digits. We do this because it turns out that the segmentation problem is not so difficult to solve once you have a good way of classifying individual digits. There are many approaches to solving the segmentation problem. One approach is to trial many different ways of segmenting the image, use the individual digit classifier to score each trial segmentation. Using the individual. A trial segmentation gets a high score if the individual digit classifier is confident of its classification in all segments, and a low score if the classifier is having a lot of trouble in one or more segments. The idea is that if the classifier is having trouble somewhere, then it's probably having trouble because the segmentation has been chosen incorrectly. This idea and other variations can be used to solve the segmentation problem quite well. So instead of worrying about the segmentation, we'll concentrate on developing a neural network which can solve the more interesting and difficult problem, namely recognizing individual handwritten digits. To recognize individual digits, we will use a 3-layer neural network. Input layer, 786 neurons. Hidden layer, n equals 15 neurons. Output layer, 10, 0 to 9. The input layer of the network contains neurons encoding the values of the input pixels. As discussed in the next section, our training data for the network will consist of many 28 by 28 pixel images of scanned handwritten digits, and so the input layer contains 784 equals 28 by 28 neurons. For simplicity, I've omitted most of the 784 input neurons in the diagram above. The input pixels are grayscale with a value of 0.0 representing white, a value of 1.0 representing black, and in between values representing gradually darkening shades of gray. The second layer of the network is a hidden layer. We denote the number of neurons in this hidden layer by n, and we'll experiment with different values for n. The example shown illustrates a small hidden layer containing just n equals 15 neurons. The output layer of the network contains 10 neurons. If the first neuron fires, i.e. has an output approximately equal to 1, then that will indicate that the network thinks the digit is a 0. If the second neuron fires, then that will indicate that the network thinks the digit is a 1, and so on. A little more precisely, we number the output neurons from 0 through 9 and figure out which neuron has the highest activation value. If that neuron is, say, neuron number 6, then our network will guess that the input digit was a 6, and so on for the other output neurons. You might wonder why we use 10 output neurons. After all, the goal of the network is to tell us which digit, 0, 1, 2, etc., 9, corresponds to the input image. A seemingly natural way of doing that is to just use 4 output neurons, treating each neuron as taking on a binary value, depending on whether the neuron's output is closer to 0 or 1. 4 neurons are enough to encode the answer, since 2 to the 4 equals 16 is more than the 10 possible values for the input digit. Why should our network use 10 neurons instead? Isn't that inefficient? The ultimate justification is empirical. We can try out both network designs, and it turns out that for this particular problem, the network with 10 output neurons learns to recognize digits better than the network with 4 output neurons. But that leaves us wondering why using 10 output neurons works better. Is there some heuristic that would tell us in advance that we should use the 10 output encoding instead of the 4 output encoding? To understand why we do this, it helps to think about what the neural network is doing from first principles. Consider first the case where we use 10 output neurons. Let's concentrate on the first output neuron, the one that's trying to decide whether or not the digit is a 0. It does this by weighing up evidence from the hidden layer of neurons. What are those hidden neurons doing? Well, just suppose for the sake of argument that the first neuron is a hidden layer. In the hidden layer, detects whether or not an image like the following is present. It can do this by heavily weighting input pixels which overlap with the image and only lightly weighting the other inputs. In a similar way, let's suppose for the sake of argument that the second, third, and fourth neurons in the hidden layer detect whether or not the following images are present. As you may have guessed, these 4 images together make up the 0 image we saw in the line of digits shown earlier. So if all of these hidden neurons are firing, then we can conclude that the digit is a 0. Of course, that's not the only sort of evidence we can use to conclude that the image was a 0. We could legitimately get a 0 in many other ways, say through translations of the above image or slight distortions. But it seems safe to say that at least in this case, we'd conclude that the input was a 0. Supposing the neural network functions in this way, we can give a plausible explanation for why it's better to have 10 outputs from the network rather than 4. If we had 4 outputs, then the first output neuron would be trying to decide what the most significant bit of the digit was, and there's no easy way to relate that most significant bit to simple shapes like those shown above. It's hard to imagine that there's any good historical reason the component shapes of the digit will be closely related to, say, the most significant bit in the output. Now, with all that said, this is all just a heuristic. Nothing says that the 3-layer neural network has to operate in the way I described, with the hidden neurons detecting simple component shapes. Maybe a clever learning algorithm will find some assignment of weights that lets us use only 4 output neurons. But as a heuristic, the way of thinking I've described works pretty well, and you can save a lot of time in designing good neural network architecture. And can save you a lot of time. Exercise. There is a way of determining the bitwise representation of a digit by adding an extra layer to the 3-layer network above. The extra layer converts the output from the previous layer into a binary representation, as illustrated in the figure below. Find a set of weights and biases for the new output layer, assuming that the first 3 layers of neurons are such that the correct output in the 3rd layer, i.e. the old output layer, has activation at least 0.99, and incorrect outputs have activation less than 0.01. Okay. So we're trying to find 4 times 10 weights and 4 biases such that we encode the binary representation of whichever input is a 1. Okay. I'm sure there's a like straightforward way to do it, but I'm gonna have to do it with a little bit of trial and error. So let's see. We've got P1, or how am I gonna do this? So let's start with X is our input. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If x of 0 equals 1, then we want 0 on here. Here's our test cases. For I in range 9. X template. Or I can just do this. X equals this. X of I equals 1. So this is the output of the neural net. Then what I want is print I and my new network. So I'll call that net dot apply X. Yeah. Okay, now I need to define net. So I'm making my own class here, def apply self x, which is an numpy.ndArray array returns another numpy.ndArray. Actually, it returns just a list of 4 floats. You're gonna have a bunch of perceptrons. So self.p1 equals, or no, they're not perceptrons, they're sigmoids. S1 equals sigmoid of some weights and biases. This needs to be an np.array. Why is it underlining this? Oh, bias. Okay, so we've got 4 sigmoids, 2, 3, 4. When you apply, you just do return self.s1.apply x. Okay, we're just doing this. And then let's declare our net. This should be an ND array. I can just do that in here. Okay, so what does that do? Well, it's not gonna work. I need these to be 9 things long. 1, 2, 3, 4, 5, 6, 7, 8, 9. I actually need them to be 10 things long. this needs to be 10. Okay. Can I just run this, first of all? Python sigmoid. Yes. So everything is 0.5. This is hard to read with the NP float 64s, so can I convert this to a regular list? NumPy convert to list. Dot to list. No. Without the underscore. Nope. Cannot access attribute to list. Oh. Wait, it already thinks it's a list. This is supposed to be returning a float, but it's returning a NumPy float 64. So let's just cast these all to floats. Okay, that's easier to read. All right, so obviously this is not working yet. So, so what am I allowed to have as my weights and my biases? Can it be any number? Positive and negative? Numbers between 0 and 1. For the weights. Or for the outputs. Oh, just the output. I think my weights and my biases could be whatever I want. So the thing is, this is the string, this is what I'm looking for, is you go 0, 0, 0, 0. This is going to be 0. Oops. Then 1 would be this. Then 2 would be this. One, 2, 3, 4, 5, 6, 7, 8, 9. 3 would be this. Or, I mean this. 4, 5, 6, 7, 8, 9. So I guess for each bit I need to check, and this can be S1, oops. S1, S2, S3, S4. So S1 should be 1. when my input is an 8 or a 9. So I'm thinking that's gonna, here, let's move this up here. S1 should be 1 when the input is an 8 or a 9. So what if I put 1s over here? S2 should be 1 when my input is a 4, 5, 6, or 7. 0, 1, 2, 3, 4, 5, 6, or 7. S4 should be 1 when the input is 2, 3, or 6, 7. 0, 1, 2, 3, 4, 5, 6, 7. And S4 should be 1 when the input is 1, 3, 5, 7, or 9. 1, 3, 5, 7, 9. So let's just see what that does without tuning the weights. So we're getting 0.5 on all of the ones that I want to be 0, I think. So can I add a bias of negative 0.5? Is that what would make sense? That didn't go all the way. Maybe a bias of negative 1. No, I'm not sure. Hold on, let's go back to just 0s and 1s. Clear, run this. Okay, so for 0 we got 0.5, 0.5, 0.5, 0.5, but we wanted 0, 0, 0, 0. When I put 0s in here, my Z is gonna be 0. So I do think I need a bias of 0.5 or negative 0.5 to get 0 to work. That does not do it. And that does not do it, but it's not doing what I'm expecting. Oh yeah, it is actually. So what about 1? That puts it at 0.2 and 0.7. What about like 99? 1.0, negative 99? That puts it at 0. But now it's always going to be 0. So it was maybe just a slight negative is good enough. So now it's 0.2. Our goal is to have, where is it? It just says converts it into a binary representation. It doesn't say how much it needs to be close to 0 and 1. So I guess like I could make these 99s and this a 99, and that should move it more, right? So now this is 0 everywhere except 8 and 9, and 8 and 9 put it at 0.5. Why 0.5 and not 0? Because it ends up right in the middle. If my bias was... So if my bias is negative 200 and... or... No. My bias is negative 50. Okay, now I've got zeros and ones. So why don't I replace all of my ones with 100s and all of my biases with negative 50? Now it's a little hard to read, so let's instead of directly printing the output, result equals this. Print int of D for D in result. That's right. All of this is right. Okay, so we did it. And what did we learn? I guess we learned how to reproduce a truth table out of sigmoids. You just put a big number as the weight wherever you want the neuron to output that based on when the input is a 1 on that one, and you get the bias to be negative half of the weight, and this works if your inputs are 1 row per the truth table. Like, or it's like when your input is exclusive, so you can't have like a 2 and a 7, otherwise that would screw it up. You have to have either 2 or 7 as the input, so only one of your inputs should be a 1 for this trick to work. But that's cool. So let's move on. Learning with gradient descent. Now that we have a design for our neural network, how can it learn to recognize digits? The first thing we'll need is a data set to learn from, a so-called training data set. We'll use the MNIST data set, which contains tens of thousands of scanned images of handwritten digits, together with their correct classifications. MNIST's name comes from the fact that it is a modified subset of 2 data sets collected by NIST, the United States National Institute of Standards and Technology. Here's a few images from MNIST, 504192. As you can see, these digits are in fact the same as those shown at the beginning of the chapter, as a challenge to recognize. Of course, when testing our network, we'll ask it to recognize images which aren't in the training set. The MNIST data comes in 2 parts. The first part contains 60,000 images to be used as training data. These images are scanned handwriting samples from 250 people, half of whom were US Census Bureau employees and half of whom were high school students. The images are grayscale and 28 by 28 pixels in size. The second part of the MNIST dataset is 10,000 images to be used as test data. Again, these are 23 by 23 grayscale images. We'll use the test data to evaluate how well our neural network has learned to recognize digits. To make this a good test of performance, the data was taken from a different set of 250 people than the original training data, albeit still a group split between Census Bureau employees and high school students. This helps give us confidence that our system can recognize digits from people whose writing it didn't see during training. We'll use the notation x to denote a training input. It'll be convenient to regard each training input x as a 28 by 28 784 dimensional vector. Each entry in the vector represents the gray value for a single pixel in the image. We'll denote the corresponding desired output by y equals y of x, where y is a 10-dimensional vector. For example, if a particular training image x depicts a 6, then y of x is equal to 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, transposed. So this is a row vector, you transpose it to get a column vector. Is the desired output from the network. Note that T is the transpose operation, turning a row vector into an ordinary column vector. What we'd like is an algorithm that lets us find weights and biases so that the output from the network approximates y of x for all training inputs to x, or all training inputs x. To quantify how well we're achieving this goal, we define a cost function. C of weights and biases is defined as 1 over 2n times the sum over all x of the absolute value of the square of the difference between y of x and a, asterisk. Sometimes referred to as a loss or objective function. We use the term cost function throughout this book, but you should note that other terminology, since it's often used in research papers and other discussions of neural networks. I think I've seen loss function used most, but again, I am not an expert. Here, W denotes the collection of all weights in the network. B, all the biases. N is the total number of training inputs. A is a vector of outputs from the network when X is the input. And the sum over all training inputs X. Of course, the output A depends on X, W, and B. But to keep the notation simple, I haven't explicitly indicated this dependence. The notation absolute value of V just denotes the usual length function for a vector V. Ah, okay, I was calling it absolute value. We'll call C the quadratic cost function. It's also sometimes known as the mean squared error, or just MSE. Inspecting the form of the quadratic cost function, we see that cost of weights and biases is non-negative, since every term in the sum is non-negative. Furthermore, the cost of weights and biases becomes small, i.e. C of WB is approximately equal to 0, precisely when y of x is approximately equal to the output A for all training inputs, x. So our training algorithm has done a good job if it can find weights and biases so that C of WB is approximately equal to 0. By contrast, it's not doing so well when C of WB is large. That would mean that y of x is not close to the output A for a large number of inputs. So the aim of our training algorithm will be to minimize the cost C of WB as a function of the weights and biases. In other words, we want to find a set of weights and biases which can make the cost as small as possible. We'll do that using an algorithm known as gradient descent. Alright, so the cost function is the sum of the distances between what we got and what we wanted. If we got what we wanted, then those distances are short. Why introduce the quadratic cost? After all, aren't we primarily interested in the number of images correctly classified by the network? Why not try to maximize the number directly, rather than minimizing a proxy measure like the quadratic cost? The problem with that is that the number of images correctly classified is not a smooth function of the weights and biases in the network. For the most part, making small changes to the weights and biases won't cause any change at all to the number of training images classified correctly. That makes it difficult to figure out how to change the weights and biases to get improved performance. If we instead use a smooth cost function like the quadratic cost, it turns out to be easy to figure out how to make small changes in the weights and biases so as to get an improvement in the cost. That's why we focus first on minimizing the quadratic cost, and only after that will we examine the classification accuracy. Even given that we want to use a smooth cost function, you may still wonder why we chose the quadratic function used in equation 6. Isn't this a rather ad hoc choice? Perhaps if we chose a different cost function, we'd get a totally different set of minimizing weights and biases. This is a valid concern, and we'll revisit the cost function and make some modifications. However, the quadratic cost function of equation 6 works perfectly well for understanding the basics of learning in neural networks, so we'll stick with it for now. Recapping, our goal in training a neural network is to find the weights and biases which minimize the quadratic cost function C of WB. This is a well-posed problem, but it's got a lot of distracting structure as currently posed. The interpretation of W and B as weights and biases, the sigmoid function lurking in the background, the choice of network architecture, MNIST, and so on. It turns out that we can understand a tremendous amount by ignoring most of that structure and just concentrating on the minimization aspect. So for now, we're going to forget all about the specific form of the cost function, the connection to neural networks, and so on. Instead, we're going to imagine that we've simply been given a function of many variables and we want to minimize that function. We're going to develop a technique called gradient descent, which can be used to solve such minimization problems. Then we'll come back to the specific function we want to minimize for neural networks. Okay, let's suppose we're trying to minimize some function C of v. This could be any real valued function of many variables, v equals v1, v2, etc. Note that I've replaced the w and b notation by v to emphasize that this could be any function. We're not specifically thinking in the neural networks context anymore. To minimize C of v, it helps to imagine C as a function of just two variables, which we'll call v1 and v2. So we've got a 3D plot. C is the height, v1 and v2 are the x and y position. What we'd like to find, or what we'd like is to find where C achieves its global minimum. Now, of course, for the function plotted above, we can eyeball the graph and find the minimum. In that sense, I've perhaps shown slightly too simple a function. A general function C may be a complicated function of many variables, and it won't usually be possible to just eyeball the graph to find the minimum. One way of attacking the problem is to use calculus to try to find the minimum analytically. We could compute derivatives and then try using them to find places where C is an extremum. With some luck, that might work when C is a function of just one or a few variables, but it'll turn into a nightmare when we have many more variables. And for neural networks, we'll often want far more variables. The biggest neural networks have cost functions which depend on billions of weights and biases in an extremely complicated way. Using calculus to minimize that just won't work. After asserting that we'll gain insight by imagining C as a function of just two variables, I've turned around twice in two paragraphs and said, hey, but what if it's a function of many more than two variables? Sorry about that. Please believe me when I say that it really does help to imagine C as a function of two variables. It just happens that sometimes the picture breaks down, and the last two paragraphs were dealing with such breakdowns. Good thinking about the mathematics involves juggling multiple intuitive pictures, learning when it's appropriate to use each picture and when it's not. Okay, so calculus doesn't work. Fortunately, there is a beautiful analogy which suggests an algorithm which works pretty well. We'll start by thinking of our function as a kind of valley. If you squint just a little at the plot above, that shouldn't be too hard. And we'll imagine a ball rolling down the slope of the valley. Our everyday experience tells us that the ball will eventually roll to the bottom of the valley. Perhaps we can use this idea as a way to find a minimum for the function. We'd randomly choose a starting point for an imaginary ball, then we'd simulate the motion of the ball as it rolled down to the bottom of the valley. We could do this simulation simply by computing derivatives, and perhaps some second derivatives of C. Those derivatives would tell us everything we need to know about the local shape of the valley, and therefore how our ball should roll. Based on what I've just written, you might suppose that we'll be trying to write down Newton's equations of motion for the ball, considering the effects of friction and gravity and so on. Actually, we're not going to take the ball rolling analogy quite that seriously. We're devising an algorithm to minimize C, not developing an accurate simulation of the laws of physics. The ball's eye view is meant to stimulate our imagination, not constrain our thinking. So rather than get into all the messy details of physics, let's simply ask ourselves, if we were declared God for a day and we could make up our own laws of physics dictating to the ball how it should roll, what laws of motion should we pick that would make it so the ball always rolled to the bottom of the valley? To make this question more precise, let's think about what happens when we move the ball a small amount, delta v1 in the v1 direction, and a small amount, delta v2 in the v2 direction. Calculus tells us that C changes as follows. Delta C is approximately equal to derivative of C with respect to v1 times the change in v1 plus derivative of C with respect to v2 times the change in v2. We're going to find a way of choosing delta v1 and delta v2 so as to make delta C negative, i.e. we'll choose them so that the ball is rolling down the valley. To figure out how to make such a choice, it helps to define delta v to be the vector of changes in v. Delta v equals delta v1, delta v2 column vector, where t is again the transpose operation, turning the row vector into a column vector. We'll also define the gradient of c to be the vector of partial derivatives. Derivative of c with respect to v1, comma, derivative of c with respect to v2, column vector. We'll denote the gradient by upside down triangle C. What is this symbol? Del. We'll denote the gradient vector by del of C, i.e. del of C is defined as the derivative of C with respect to V1, comma, the derivative of C with respect to V2, column vector. Okay, I'm gonna pause here just to make sure I understand what we're talking about so far. So we've got two different triangles of C. Delta C is a small change in the cost function. If our changes are small, then calculus tells us that this approximate relationship holds. So the change in the output is approximately equal to the amount that you changed each of the v's times the gradient, or the slope of the cost function in the direction of that v. The reason for that is that if the cost function is a super wavy and crazy shape, when you zoom way in, it'll get less wavy and less crazy. When you zoom, you can zoom all the way in to the point where the cost function is just a plane. Like no matter where you zoom in, as long as the function is continuous, I think, eventually you'll get to a point where the function is just a plane. You'll have to just picture zooming in your head, because I'm not able to show this. And then once it's just a plane, then when you move in the x direction, you just go up by however much the plane is inclined in the x direction. If you move in the y direction, you just go up by however much the plane is inclined in the y direction. And so if you zoom in far enough, then this is true. Like the derivative of c with respect to v is the slope in the v direction. The derivative of c with respect to vi is the slope of c in the I direction. So how much do you move in the I direction times how much is it sloping in that direction. And I guess if you zoomed in infinitely far, then this would be an equality. But because we're always dealing with some small amount, but not infinitely small, this is approximately. So this is like, you've zoomed in super duper far, but not infinitely far. So it's kind of like a plane, but it's not exactly a plane. Okay, that's what. So we can say that the change in c is proportional to, or is about equal to this formula. Grad of c, the gradient vector of c, which is a different triangle in front of c, is the partial derivatives. So that's these components. So I can tell what's going to happen next is we're going to have a dot product between grad of c and delta v, because that's what's going to give us this. So we're going to have delta c is going to be approximately equal to dot product between grad of c and delta v. So let's go. In a moment, we'll rewrite the change in delta C in terms of delta V and the gradient grad of C. Before getting to that though, I want to clarify something that sometimes gets people hung up on the gradient. When meeting the grad of C notation for the first time, people sometimes wonder how they should think about the grad or del symbol. What exactly does del mean? In fact, it's perfectly fine to think of del of C as a single mathematical object, the vector defined above, which happens to be written using two symbols. In this point of view, del is just a piece of notational flag waving, telling you, hey, del of C is a gradient vector. There are more advanced points of view where del can be viewed as an independent mathematical entity in its own right. For example, a differential operator, but we won't need such points of view. With these definitions, the expression 7 for del or delta C can be rewritten as, and this is what I was predicting, delta C is approximately equal to grad of C dot product delta V. This equation helps explain why grad of C is called the gradient vector. Grad of C relates changes in V to changes in C, just as we'd expect something called a gradient to do. But what's really exciting about the equation is that it lets us see how to choose delta V so as to make delta C negative. In particular, suppose we chose delta V equals negative, how do I pronounce this symbol? Eta. Delta V equals negative eta times grad of C, where eta is a small positive parameter known as the learning rate. Then equation 9 tells us that delta C is approximately equal to negative eta times grad of C dot product grad of C, which is equal to negative eta times absolute value of grad of C squared, or length of grad of C squared. Because grad of C squared is greater or equal to 0, this guarantees that delta C is less than or equal to 0. Yes, this is a length, so it is non-negative. So if you multiply it by something negative, then the result will be negative. This guarantees that delta C is less than or equal to 0, i.e. C will always decrease, never increase, if we change V according to the prescription in 10. Within, of course, the limits of approximation in equation 9. This is exactly the property we wanted, and so we'll take equation 10 to define the law of motion for the ball in our gradient descent algorithm. That is, we'll use equation 10 to compute a value for delta V, then move the ball's position V by that amount. So V goes to V prime, and V prime is equal to V minus eta times grad of C. Then we'll use this update rule again to make another move. If we keep doing this over and over, we'll keep decreasing C until, we hope, we reach a global minimum. Summing up, the way the gradient descent algorithm works is to repeatedly compute the gradient grad of C and then move in the opposite direction, falling down the slope of the valley. We can visualize it like this. Okay, very helpful. Arrow pointing down. Notice that with this rule, gradient descent doesn't reproduce real physical motion. In real life, a ball has momentum, and that momentum may allow it to roll across the slope, or even momentarily roll uphill. It's only after the effects of friction set in that the ball is guaranteed to roll down into the valley. By contrast, our rule for choosing delta V just says, go down right now. That's still a pretty good rule for finding the minimum. To make gradient descent work correctly, we'll need to choose the learning rate, eta, to be small enough that equation 9 is a good approximation. If we don't, we might end up with delta C greater than 0, which obviously would not be good. Okay, so eta needs to be small because eta tells you how much to move, and this equation is only true if the amount you move is small. So if you're super zoomed in, it's a plane. If you're not zoomed in far enough, then then it's not a plane, it's some other crazy shape. At the same time, we don't want eta to be too small, since that will make the changes in delta v tiny, and thus the gradient descent algorithm will work very slowly. In practical implementations, eta is often varied so that equation 9 remains a good approximation, but the algorithm isn't too slow. We'll see later how this works. I've explained gradient descent when c is a function of just 2 variables, but in fact everything works just as well when c is a function of many more variables. Suppose in particular that c is a function of m variables, v1 up to vm. Then the change delta c in c produced by a small change delta v equals delta v1, etc. up to delta vm, all that as a column vector, is delta c approximately equal to grad of c dot product delta v, where the gradient grad of c is the vector. Grad of c is defined as each component of a column vector is the gradient with respect to the gradient of c with respect to that direction of that v. Just as for the 2 variable case, we can choose delta v equals negative eta grad of c, and we've guaranteed that our approximate expression 12 for delta c will be negative. This gives us a way of following the gradient to a minimum, even when c is a function of many variables, by repeatedly applying the update rule. V goes to v prime, which is equal to v minus eta grad of c. You can think of this update rule as defining the gradient descent algorithm. It gives us a way of repeatedly changing the position v in order to find a minimum of the function c. The rule doesn't always work. Several things can go wrong and prevent gradient descent from finding the global minimum of c. A point we'll return to and explore in later chapters, but in practice, gradient descent often works extremely well, and in neural networks we'll find that it's a powerful way of minimizing the cost function, and so helping the net learn. Indeed, there's even a sense in which gradient descent is the optimal strategy for searching for a minimum. Let's suppose that we're trying to make a move, delta v, in a position so as to decrease c as much as possible. This is equivalent to minimizing delta c approximately equal to grad of c dot product delta v. We'll constrain the size of the move so that the length of delta v is equal to epsilon for some small fixed epsilon greater than 0. In other words, we want a move that is a small step of a fixed size, and we're trying to find the movement direction which decreases c as much as possible. It can be proved that the choice of delta v which minimizes grad of c dot product delta v is delta v equal to negative eta grad of c, where eta equals epsilon over length of delta grad of c is determined by the size constraint length of delta v equals epsilon. So gradient descent can be viewed as a way of taking small steps in the direction which does the most to immediately decrease c. I thought this was going to happen. Okay. So it makes sense. It's like grad of c tells you the direction. Grad of c tells you the slope. If the amount that we're going to move is not in our control, and the only thing we can pick is the direction, you're going to pick the direction that minimizes the slope. Okay. Okay, we've got some exercises in the middle of the chapter, so let's go through these. Prove the assertion of the last paragraph. Hint, if you're not already familiar with the Cauchy-Schwarz inequality, you may find it helpful to familiarize yourself with it. Okay. So the assertion is the movement direction which minimizes c as much as possible is delta v equals to negative epsilon over, here, this is what's a good way to do this? I want to open up a. Let's see if I'm able to just write it. I'm not sure if this will make enough sense, but well, actually, can I do this? All right, I can have some symbols in my code. And I'll make a new file here, proof.txt. Okay, so the claim is if we want to minimize this, if we want to minimize here, with a delta v, or length of delta v equals epsilon, just call it eps. The best value is this. Or yes, but then also eta is equal to this. So this is minus eps this over the length of delta C. Okay, so I guess the two things to show are length is epsilon, and no other direction would be smaller, or yeah, would minimize this more. So the first one is just saying what's the length of this thing. So if I take the length of this whole thing, I can move the constants out of it. So that's a constant. That's a constant. I can't move the negative out of it because the negative goes away once you take a length. But yeah, the negative goes away, so I can just remove it, and then this simplifies to 1. So this is proved. That no other direction would be smaller, we're going to have to learn the Cauchy-Schwarz inequality. Okay, so So we're trying to show that there's no other v that would be bigger than this. Or smaller than this, I mean. Where v is this thing. So here I can simplify that. This is going to be, and this can come out also. Well, whatever, it can just be out here. Grad of C dot producted with grad of C looks like some of the stuff here. So the length is equal to the square root of the inner product with itself. I know a dot product is an inner product. So this is equal to or wait, what am I trying to say? It's I want to remove the dot product here and turn it into an absolute value thing, a length. So U is dot producting itself. Grad C is equal to this, which means if you took the square on the other side, you would say U squared is equal to U dot U. So this is the same as this squared. And then two of them cancel out and you end up with this. So the amount we moved was negative epsilon times the length of grad C. And I want to show that we couldn't have moved any farther than that. I'm not exactly sure how the Cauchy-Schwarz inequality comes in yet. Okay, well, why don't we write this thing, the Cauchy-Schwarz inequality for this thing. So this is less than or equal to length of C times length of V. Length of V, we don't get to choose, it's epsilon. Okay, well there it is. And then this is equal to that. So we showed that we know that you can't do better than this. You can't get smaller than this. Or wait, I guess we showed that wait, did I just show the opposite somehow of what I meant to show? And I lost the negative somehow. Wait, how does this, let me do this one again. So we have this. We know that this is less than or equal to the length of one times the length of the other. That's what this is saying. Oh, the length of the left side. Or is this a length or an absolute value? I think that's an absolute value. So this is what we know. We know delta V is just epsilon, so we can move the epsilon out here. Okay, so if the absolute value is less than this, that means we have two equations. We have, if it's positive, it's less than or equal to that. If it's negative, it's greater or equal to that, right? And we're looking for something negative because we're trying to minimize. So we've shown we know that V, or that this thing, delta C, is greater or equal to this. Sorry, I needed a negative here, didn't I? I'm getting confused with the absolute value. Let me just write it one more time. So this is equal, or is less than or equal, this is by Cauchy-Schwarz. This is less than or equal to the length of both sides. We know this is epsilon. And this is absolute value is equal to length of both sides. Okay. So if this thing, if delta C is positive, then this is true. The other direction, I don't know why I'm having a lot of trouble thinking about it. What's the right way to remove an absolute value? So I can just write it out. So it means that this and this are both true, right? And then how do you multiply by -1 on both sides of an inequality? Do you have to flip the direction of it? I think you do. So we do end up with this. We know that it's that it has to be greater or equal to this, and we found a way to make it equal to this. So that means that this is the best you can do. Okay, there's our proof. Back to the book. I explained gradient descent when c is a function of two variables, and when it's a function of more than two variables, what happens when c is a function of just one variable? I read that in a weird way, but you get it. Can you provide a geometric interpretation of what gradient descent is doing in the one-dimensional case? Yeah, when you zoom way in, instead of seeing a plane, you see a line. And so you're moving either left or right, and then you're multiplying the amount you moved by the slope to get the change in c, because that's how slopes work. The change in height is going to be the slope times the change in like x. So that's that. All right, moving on. People have investigated many variations of gradient descent, including variations that more closely mimic a real physical ball. These ball mimicking variations have some advantages, but also have a major disadvantage. It turns out to be necessary to compute second partial derivatives of c, and this can be quite costly. To see why it's costly, suppose we want to compute all the second partial derivatives. Second derivative of c with respect to Vj and Vk, or I guess this is, yeah, it's Yeah, I don't know how else to say that. If there are a million such Vj variables, then we'd need to compute something like a trillion, i.e. a million squared, second partial derivatives. That's going to be computationally costly. With that said, there are tricks for avoiding this kind of problem, and finding alternatives to gradient descent is an active area of investigation. But in this book, we'll use gradient descent and variations as our main approach in learning neural networks. Asterisk. Actually more like half a trillion, since the derivative of c with respect to Vj Vk equals the derivative of c with respect to Vk Vj. Still, you get the point. How can we apply gradient descent to learn in a neural network? The idea is to use gradient descent to find weights Wk and biases Bl, which minimize the cost in equation 6. To see how this works, let's restate the gradient descent update rule with the weights and biases replacing the variables Vj. In other words, our position now has components Wk and Bl, and the gradient vector grad of c has corresponding components derivative of c with respect to Wk and derivative of c with respect to Bl. Writing out the gradient descent update rule in terms of components, we have W of k goes to W prime of k, which is equal to W of k minus eta times grad of c with respect to Wk. B of L, or Bl, goes to B prime L, which is equal to Bl minus eta times derivative of c with respect to Bl. So this is the same as what we saw before, but B and W are replacing V. By repeatedly applying this update rule, we can roll down the hill and hopefully find a minimum of the cost function. In other words, this is a rule which can be used to learn in a neural network. There are a number of challenges in applying the gradient descent rule. We'll look into those in depth in later chapters. But for now, I just want to mention one problem. To understand what the problem is, let's look back at the quadratic cost in equation 6. What happens if I click this? Okay. Equation 6 is the quadratic cost formula. Cost of WB is defined as 1 over 2n times the sum over x of the distances between the what we wanted and what we got squared. Notice that this cost function has the form c equals 1 over n times sum over x of cx. That is, it's an average over costs. Cx is defined as the square of the distance between what we got and what we wanted over 2 for individual training examples. In practice, to compute the gradient grad of c, we need to compute the gradients grad of cx separately for each training input x and then average them. Grad of c equals 1 over n times the sum over x of grad of cx. Unfortunately, when the number of training inputs is very large, this can take a long time and learning thus occurs slowly. An idea called stochastic gradient descent can be used to speed up learning. The idea is to estimate the gradient grad c by computing grad cx for a small sample of randomly chosen training inputs. By averaging over this small sample, it turns out we can quickly get a good estimate of the true gradient grad c, and this helps speed up gradient descent and thus learning. To make these ideas more precise, stochastic gradient descent works by randomly picking out a small number m of randomly chosen training inputs. We'll label those random training inputs x1, x2, etc., xm, and refer to them as a mini-batch. Provided the sample size m is large enough, we expect that the average value of grad of cxj will be roughly equal to the average overall grad of cx. That is, the sum from j equals 1 to m of grad of cxj over m is approximately equal to the sum over x of grad of cx over n equals grad of c, where the second sum is over the entire set of training data. Swapping sides, we get grad of c is approximately equal to 1 over m sum from j equals 1 to m of grad of cxj. Confirming that we can estimate the overall gradient by computing gradients for just the randomly chosen mini-match. Okay. So x, this capital X is a training input. We were using lowercase x for this before, but now it's capital X1, X2, etc. We're saying here that if we have a big sample size, then the gradient of the loss function on that sample size should be about equal to the gradient of the average gradient over a big sample should be approximately equal to the average gradient over the whole thing. That kind of makes sense. Confirming that we can estimate the overall gradient. Okay. To connect this explicitly to learning in neural networks, suppose WK and BL denote the weights and biases in our neural network. Then, stochastic gradient descent works by picking out a randomly chosen mini batch of training inputs and training with those. WK goes to W prime K, which is equal to WK minus eta over M times sum over J of gradient of Cxj over, with respect to WK. Then WB equals B prime of L, B of L equals B prime, or goes to B prime of L, which is equal to B of L minus eta over M times sum over J of the cost of xj with respect to, or the gradient of the cost of xj with respect to BL. Okay, so this is saying, here's how you update your weight. If you're looking at a specific weight, WK, the way you update it is you grab a batch of samples, you see how you do on those samples. So that's what the CXJs are. Then you figure out the gradient of the cost function with respect to the weight that you're talking about. So this is saying like, what direction should I move the weight to make it smaller? So you take the sum of all the directions that you should move the weight to make it smaller, multiplied by eta, which is how much you should move. So direction times how much you should move, over m, because we're taking an average over m samples. Same for bias. Where the sums are over all the training examples xj in the current mini batch. Then we pick out another randomly chosen mini batch and train with those, and so on until we've exhausted the training inputs, which is said to complete an epoch of training. At that point, we start over with a new training epoch. Incidentally, it's worth noting that conventions vary about scaling of the cost function and of mini-batch updates to the weights and biases. In equation 6, which is this, we scaled the overall cost function by a factor 1 over n. People sometimes omit the 1 over n, summing over the costs of individual training examples instead of averaging. This is particularly useful when the total number of training examples isn't known in advance. This can occur if more training data is being generated in real time, for instance. And in a similar way, the mini-batch update rules 20 and 21 sometimes omit the 1 over m term out in front of the sums. Conceptually, this makes little difference since it's equivalent to rescaling the learning rate eta. Ah, okay. But when doing detailed comparisons of different work, it's worth watching out for. We can think of stochastic gradient descent as being like political polling. It's much easier to sample a small mini batch than it is to apply a gradient descent to the full batch, just as carrying out a poll is easier than running a full election. For example, if we have a training set of size n equals 60,000, as in MNIST, and choose a mini batch size of, say, m equals 10, this means we'll get a factor of 6,000 speed up in estimating the gradient. Of course, the estimate won't be perfect. There will be statistical fluctuations, but it doesn't need to be perfect. All we really care about is moving in a general direction that will help decrease C. And that means we don't need an exact computation of the gradient. In practice, stochastic gradient descent is a commonly used and powerful technique for learning in neural networks, and it's the basis for most of the learning techniques we'll develop in this book. Exercise. An extreme version of gradient descent is to use a mini batch size of just 1, that is, a training input. Given a training input x, we update our weights and biases according to the rules wk goes to w prime k, which is equal to wk minus eta times derivative of c of x with respect to wk. And these are so hard to say out loud. BL goes to B prime L, which is equal to BL minus eta times the gradient of CX with respect to BL. Then we choose another training input and update the weights and biases again, and so on repeatedly. This procedure is known as online, or incremental learning. In online learning, a neural network learns from just one training input at a time, just as human beings do. Name one advantage and one disadvantage of online learning compared to stochastic gradient descent with a mini batch of, say, 20. Okay, hopefully these are, I don't know if these are the advantages and disadvantages that he's thinking of, but advantage is that it'll be faster because you have less stuff to compute. Disadvantage is it'll be less accurate because the statistical fluctuations will be better. But a single example is a worse approximation of the full gradient than, 20 examples. Another advantage, though, is like you could learn in real time. Like you can immediately improve from an example that was just generated 1 second ago. It's hard to think of like why that would be helpful, but yeah. Let me conclude this section by discussing a point that sometimes bugs people new to gradient descent. In neural networks, the cost C is, of course, a function of many variables, all the weights and biases, and so, in some sense, defines a surface in a very high-dimensional space. Some people get hung up thinking, hey, do I have to visualize all these extra dimensions? And they may start to worry. I can't think in 4 dimensions, let alone 5 or 5 million. Is there some special ability they're missing? Some ability that real super mathematicians have? Of course the answer is no. Even most professional mathematicians can't visualize 4 dimensions especially well, if at all. The trick they use, instead, is to develop other ways of representing what's going on. That's exactly what we did above. We used an algebraic rather than visual representation of delta C to figure out how to move so as to decrease C. People who are good at thinking in high dimensions have a mental library containing many different techniques along these lines. Our algebraic trick is just one example. Those techniques may not have the simplicity we're accustomed to when visualizing 3 dimensions, but once you build up a library of such techniques, you can get pretty good at thinking in high dimensions. I won't go into more detail here, but if you're interested, then you may enjoy reading this discussion of some of the techniques professional mathematicians use to think in high dimensions. While some of the techniques discussed are quite complex, much of the best content is intuitive and accessible and could be mastered by anyone. I'm not going to dive into the discussion. All right. Now we're getting into the coding, the actual implementing. Implementing our network to classify digits. All right, let's write a program that learns to recognize handwritten digits using stochastic gradient descent and the MNIST training data. We'll do this with a short Python 2.7 program, just 74 lines of code. No, we will not. We're not going to be using Python 2.7. We're not going to be using this book's code. We're going to write everything from scratch. The first thing we need is to get the MNIST data. If you're a Git user, you can obtain the data by cloning the code repository for this book. Okay, we can do that. Or you can download the data and code here. No, we're gonna clone the repo. Data. That's a gzip. Okay. Incidentally, when I described the MNIST data earlier, I said it was split into 60,000 training images and 10,000 test images. That's the official MNIST description. Actually, we're going to split the data a little differently. We'll leave the test images as is, but split the 60,000 image MNIST training set into two parts, a set of 50,000 images, which we'll use to train our neural network, and a separate 10,000 image validation set. We won't use the validation data in this chapter, but later in the book we'll find it useful in figuring out how to set certain hyperparameters of the neural network, things like the learning rate and so on, which aren't directly selected by our learning algorithm. Although the validation data isn't part of the original MNIST specification, many people use MNIST in this fashion, and the use of validation data is common in neural networks. When I refer to the MNIST training data from now on, I'll be referring to our 50,000 image dataset, not the original 60,000 image dataset. Footnote. As noted earlier, the MNIST dataset is based on two datasets collected by NIST, the United States National Institute of Standards and Technology. To construct MNIST, the NIST datasets were stripped down and put into a more convenient format by Yann LeCun, Corina Cortez, and Christopher J.C. Burgess. See this link for more details. The dataset in my repository is in a form that makes it easier to load and manipulate the MNIST data in Python. I obtained this particular form of the data from the LISA Machine Learning Laboratory at the University of Montreal link. Which is a dead link. Okay. All right, well, I guess one thing I'm interested in is instead of using his version of it, can we just use the standard MNIST data? MNIST data. There's something called Python MNIST. MNIST data parser. What's eMNIST? Download a raw data set from Google Drive. I'm curious what the... Because I know that people use MNIST. Everyone uses MNIST as like the basic example whenever they're doing any neural network thing or any kind of learning thing. But I don't know like what's the main way that people get it, and what's the main format and stuff. Not found on Jan LeCun's website. What happens if I click download? I guess like this was the first result on Google for MNIST. See sample MNIST reader, but I can't click on it. No, I have to view more and then I can click on it. Huh. Because if I download this, what is code? That's not a, okay. This is people have written stuff using this data. Python MNIST, there was that that library we saw. But what is this? Is eMNIST, an extended MNIST database. It has letters and digits and stuff. It looks like it has the original 70,000. So how do I get it? Or I guess that's what this Python project does. Is this what we were looking at? Yeah. Okay, I mean, I guess we can use this. So let's get out of here. Let's actually remove the books version of this. Why would I git clone the repo? Is that just to run these scripts? Okay, sure. Git clone this, cd this, bin mnist get data. That did not work. Data, empty. Okay, what was the problem? It's trying to download from Yan LeCun. But did that not work? It doesn't say that it didn't work. Does it? It's just downloading index.html. .404 on robots. I don't even know why it's trying to download robots. I think this might just not work. Okay, RM Python mnist. This isn't going well so far. I just want to get mnist data. Well, I guess there's the Kaggle version. So why don't we try this? Don't download it to downloads, though. Download it to right here. Okay, we have the data set now. Now how do I work with it? How to read. Why is it so weird? I wonder if the Python library that we were looking at would work. Python mnist. Or no, because that was not even the same data set actually. Okay, so I guess, am I just supposed to copy this whole thing? It's split into cells, which is annoying. Because I'm not going to be running this in a Jupyter notebook. And what's all this stuff? Like, do I have those things? What's in the zip? I guess I do have those things. What are they? Train images, train labels. And then T10K images, T10K labels. Why do they have such weird names? So I'm guessing the training images is the 60,000 and the T10K is the 10,000. This is so annoying. Like X train, Y train. I don't know what these things mean. What about the other thing we were looking at? Python MNIST. Now that I have the data, you're supposed to be able to just do this. This is so annoying. Alright, let's try it. Pip install Python MNIST. And then let's try having a main.py, or we'll just call it test.py, MNIST test. Let's do this. And let's just try to run that. Python MNIST test. I didn't give it the directory, obviously. This should be MNIST data. Is that what it's called? MNIST dash dataset. MNIST dataset slash train labels idx1 dash ubyte is a directory. MNIST dataset. Train labels idx1 dash ubyte is a directory. Well, it's also not a directory. I don't know why it extracted like this. What if I just delete the directories? File not found. Train dash labels dash idx1 dash ubyte. What if I give them dashes? That did stuff. Print len of images. 60,000. Load training, load testing. 10,000. Okay. Okay, it took some wrangling, but we have the data. And yeah, we have the data. Okay, back to here. Let's close this. So and we want to split 10,000 of it into something, into validation is what they call it. So I guess we can rename this from mnist test, to mnist. Just call it mnist. We can't call it mnist. That's already the name of the library. We'll call it mnist data, or just data loader. Then we're going to export from this. Get training, get validation, and get test. So that is just going to be def get training. Hold on, I can do this a little better. Class data loader load dir string, which defaults to being this. Just does this. Self.data equals this. And then put a self on here. Then we've got def get training, which will be this. So we're actually only exporting data loader. Self, and that's it. And then actually this is what I want. Load training. We don't need the self here. Load training, load testing. What did they call this? NMNist or something? NM data, and NM data equals this. Okay, this is going to start to make sense in a second. I'm just going to say all data equals this. I don't know what the format of these things are. We should test that actually. Let's test that right now. So print type of images and type of labels, and then just do data loader dot load. It's not called MNIST test anymore, it's called data loader. It's a list and an array. A list of what though? Print type of images of 0 and array of labels of 0. So this is a list of or let's do all images is a list of list and then of what? Whereas all labels is a list of int. What's wrong with this? Oh, because I don't know it's of what yet. Let's find out. List of int, so that was right. So these are images, these are labels. Why is it a list of ints? Aren't they? I thought the images were supposed to be grayscale. Is that wrong? Are they black and white? Maybe they're black and white. What if you print me the first image? What does it look like? Or wait, this would be the first image. Oh, it's grayscale from 0 to 255 or 256. Okay. All right, so load training, load testing. The format that they have for training and testing is not the format that the book wants us to use. The book wants us to have 50,000 training, 10,000 validation, 10,000 testing. So, so we're going to do this. Property. We're not even going to do get training because it's not actually doing anything. It's just going to return self.allImages. Give me the first 50,000. You can put underscores in Python integers to make it easier to read the 1,000 separators. List of int. return this. And what's wrong with this? Because I didn't say that it's self. Okay, so this is training. Actually, this is a tuple, which has the images and the labels. So the labels are a list of int. And what's wrong with this? Yeah, okay. Training, validation, and testing. So okay, so the validation set is from 50,000 to 60,000. And the testing is from 60,000 to 70,000. Then I just want to extend this each time. So self.all images. Oh wait, but this is an array, right? The labels are an array? I'll have to convert them to a list. All images equals, or plus equals images. All labels plus equals list of labels. These are training images, training labels. These are test images, test labels. Okay, now if I do data equals this, data.load, data.training, len of data.training, len of data.validation, len of data.test, I should see 50,000, 10,000, 10,000. I have to print these, obviously. Two. That's not what you want to see. These are tuples. So these are the things I wanted to look at. 50, 10, 10. That's what I was hoping for. And then the labels. Good. Okay. So we've got a data loader. Um, so let's get back to the book, I guess. Apart from the MNIST data, we also need a library called NumPy. Done. For doing fast linear algebra. If you don't already have NumPy installed, you can get it here. Let me explain the core features of the neural network's code before giving a full listing below. The centerpiece is a network class, which we use to represent a neural network. Here's the code we use to initialize a network object. In this code, the list sizes contains the number of neurons in the respective layers. So for example, if we want to create a network object with 2 neurons in the first layer, 3 neurons in the second layer, and 1 neuron in the final layer, we do it with this code, network 231. Okay, let's network.py, class network, init, self and sizes. Sizes is a list of integers. So self.sizes equals sizes. We're going to want to export this. I know you don't have to do this in Python, but I think it's good practice, and then you can use tools like what is it called, CAC, to enforce the public and private interfaces or like exports. So we're also going to need from NumPy import or import NumPy as NP. Self.weights equals np.random.random number between, what is this saying? It's not between y and x. It's a matrix, a y by x matrix for xy in zip sizes, -1, sizes 1. Self.biases equals np.random.rand n y1 for y in sizes 1. Okay. I don't actually like what I'm doing right now. I don't want to just be copying the code without understanding it. So I think I am not going to keep doing this. I think I'm just going to read, ignore the code blocks, and try to implement something that makes sense to me, because this does not make sense to me. So that's the last time we're going to do that. In this code, the list sizes contains the number of neurons in the respective layers. So for example, if we wanted to create a network object with 2 neurons in the first layer, 3 neurons in the second layer, and 1 neuron in the final layer, we do it with this code, 231. The biases and weights in the network object are all initialized randomly using the numpy np.random.randn function to generate a Gaussian distribution with mean 0 and standard deviation 1. This random initialization gives our stochastic gradient descent algorithm a place to start from. In later chapters, we'll find better ways of initializing the weights and biases, but this will do for now. Note that the network initialization code assumes that the first layer of neurons is an input layer and omits to set any biases for those neurons, since biases are only ever used in computing the outputs from later layers. but we didn't. So that's what this slice starting at 1 means. And then the weights are a matrix. And these ones do include the first layer. I guess because there's a weight for each input, even though there isn't a bias for each input. Okay. Note also that the biases and weights are stored as lists of NumPy matrices. So for example, net.weights_1 is a NumPy matrix storing the weights connecting the second and third layers of neurons. It's not the first and second layers, since Python's list indexing starts at 0. Since net.weights_1 is rather verbose, let's just denote that matrix W. It's a matrix such that WJK is the weight for the connection between the kth neuron and in the second layer, and the jth neuron in the third layer. This ordering of the J and K indices may seem strange. Surely it'd make more sense to swap the J and K indices around. The big advantage of using this ordering is that it means that the vector of activations of the third layer of neurons is A' equals sigmoid of WA plus B. Okay, let me try to understand this before scrolling down and having him explain it. So a single entry in the matrix is a weight. It's the W of JK is the weight between the kth neuron in the second layer and the jth neuron in the third layer. And then we're saying that the vector of activations of the third layer is this. So A' must mean the activation of this layer, and A must be the activation of the previous layer. So the activation of this layer is equal to sigmoid so the thing is, these are vectors now. Before, when we were using sigmoid, it was acting on a single the output of the sigmoid was a single number. But here the output is going to be a vector, and we're doing one sigmoid per entry in the column vector. So sigmoid of W times A, so W is a list of weights. W is the weights what is W? W is a matrix. W is a matrix where each of the, so like here, we've got A1, so we've got this big column vector. Each row here is a sigmoid neuron. So each of the sigmoid neurons is taking every output from the last row. Wait, so this column, the rows, I'm mixing up what's a, okay. A single sigmoid neuron uses all of the activations from the last row. So that's a vector of A's. And for that single sigmoid, it has it has the same number of weights. So for each sigmoid, you're doing a dot product between two vectors. Then when you extend that to being a whole list of sigmoids, you're doing a matrix multiplication between a matrix and a vector. Okay, I think I get it. Let's see. There's quite a bit going on in this equation, so let's unpack it piece by piece. A is the vector of activations of the second layer of neurons. To obtain A prime, we multiply A by the weight matrix W and add the vector B of biases. We then apply the function sigmoid element-wise to every entry in the vector WA plus B. This is called vectorizing the function sigmoid. It's easy to verify that equation 22 gives the same result as our earlier rule, equation 4, for computing the output of a sigmoid. Exercise: write out equation 22 in component form and verify that it gives the same result as the rule 4 for computing the output of a sigmoid neuron. Okay, so equation 22, A prime, I'm gonna, let's open up our proof thing again. A prime is equal to sigmoid, I'm just gonna copy this. This is like a dot product. Or no, this is a matrix multiplication. Okay, so let's write this out as a bunch of different things. So this is saying for A prime of I, you take a sigmoid of a single number, Wi dot product A of I plus B of I. This is a dot product. So I'm just, or how do I actually say this? This is a row from the matrix. A is not of I, A is just A. A uses all of the activations from the last layer. So B of I, the activation from the ith neuron, for the ith neuron of column 3, you have this. Because if you take the row of a matrix, dot product a vector, like you basically do this for each row of the matrix and sum them in order to get A, in order to get the vectorized result. So sum over I of this equals sum over I of this. Right? I'm gonna omit the sum over I parts. So this is for one sigmoid neuron. And but that's what we had to show, right? Equation 4. Oh. Yeah, this is just sigmoid of... of this. So this dot product is this sum, and then you when you have plus b and you take sigmoid of it, you get that. All right, I'm not sure that I did what it wanted me to do exactly, but I'm convinced that it's true. With all this in mind, it's easy to write code computing the output from a network instance. We begin by defining the sigmoid function. Okay, I want to write my own code for the output. So we've got apply self to, we have our input x, which is a list of integers. I mean, they're kind of floats between 0 and 1. I don't know which format it's going to use. Let's use float. And you get back a list of float. But we're not actually going to use lists of floats. We're going to use NumPy arrays, ND array. So for the first layer, you multiply the weights. So this times x plus self.biases of 0, sigmoid of that. This is your next thing. This is the next layer. We're gonna go for I in range len of either weights or biases. It's the same. Weights of I, biases of I. Let's copy this sigmoid from out here. From math import E. Okay, it starts at x, but then you have to keep, so I guess like my new x will be that, and then at the end you return whatever x was at the end. Now this sigmoid wants to act on a float, but I want it to act on a vector. So I wonder if I can just do power of a vector and NumPy will understand what to do. Net equals network of three, two, one. Print net dot apply np.array, you know, 0.3, 0.3, 0.3. Python network. Okay. So I'm trying to do a matrix multiplication here. NumPy matrix multiplication. Matmul or the at operator. Okay, so at. Well, it didn't crash. It gave me an output of size 2 instead of size 1. Because shouldn't there only be one output if I do this? What if I added more? Will that change anything? Oh, wait. Huh. Why is it giving me it's not giving me the right shape of the output. It's giving me a 1x2 instead of a 1x1. So these things are not... I don't even know what could cause that. What is x starting as? 0.3, 0.3, 0.3. And then print it after each transformation. 0.3, 0.3, 0.3. And then it's a 2x2. But x should always be a vector. Is it like I need to do this? No. All right, for in the loop, tell me what self.weights of I is, and then what x is, and then what b is. So weights is a 2x3. Hold on. Print len of self.weights and len of self.biases. 2 and 2. That makes sense. Weights is a, and then why don't you print me just the shape of them? I think you can do dot shape in NumPy. X dot shape, biases dot shape. One by two. But it's not 1x2. We saw that it was 2x3. Is this like 0 indexed or something? Wait, I'm confused. Wait, and then this is 3 by nothing. I guess that's expected. It's a vector. So 2 by 3. And then the bias is 2 by 1? Oh yeah, by 1. So if you're not by anything, you're by 1. So when these multiplied together, you end up with a 2 by 1. And then you add a 2 by 1 to that, and you still have a 2 by 1. Then in the next layer, why is x 2 by 2 all of a sudden? That doesn't make sense, does it? Print x dot shape. We end with 1 by 2. So x starts as 3 by 1, and then it becomes 2 by 2, which is wrong, and then it becomes 1 by 2, which is wrong. It should always be a vector. So where does it lose its shape? This should be 2 by 1 plus 2 by 1 should be 2 by 1, but it's ending up as 2 by 2. Is it like operator precedence or something? No? Is the sigmoid screwing it up? What if I remove the sigmoid? No. Okay, at what point are you getting screwed up? So print this dot shape. 2 by 1. That's good. And then if you do plus biases, 2 by 2, that's bad. So doing plus bias screwed it up? A 2 by nothing plus a 2 by 1 became a 2 by 2. What if I just force... Can I do x dot reshape? X dot shape of 0 and then 1? Is that a thing? Would I have to say x equals that? Yes. Now it's 3 by 1 instead of 3 by nothing. And now I'm getting everything I expect. So that's weird. Yeah, I'm getting at least I'm getting the right shape now. Yeah, 5 outputs. Okay, that's weird that that 3 by nothing is different than 3 by 1. It's like, this might not be the right way to write an array. Would I have to do like this and then dot t for transpose? That's not how you is that how you transpose? Oh, dot t on the array. That works, and then does that let me avoid having to reshape? Yeah. Huh. Okay. So far it seems like it works. I don't have a real test yet though. Note that when the input z is a vector or numpy array, numpy automatically applies the sigmoid element-wise, that is in vectorized form. Good. We then add a feed-forward method to the network class, which, given an input A for the network, returns the corresponding output. That's what we just did. All the method does is apply equation 22 to each layer. Yes. Okay, they used dot instead of the at symbol. They zipped the biases and the weights, which is actually a nicer way to do it than what I did. So let's do that also. For B, or for WB in zip self.weights self.biases WB. Okay. Of course, oh wait, I missed a footnote here. It is assumed that the input A is an n by 1 numpy nd array, not an n by nothing vector. There we go. That was exactly the problem we were running into. Here, n is the number of inputs to the network. If you try to use an n by nothing vector as input, you'll get strange results. Although using an n by nothing vector appears the more natural choice, using an n by 1 nd array makes it particularly easy to modify the code to feed forward multiple inputs at once, and that is sometimes convenient. Okay, of course the main thing we want our network to do is learn. To that end, we'll give them an SGD method which implements stochastic gradient descent. Here's the code. It's a little mysterious in a few places, but I'll break it down below after the listing. So how do we want to deal with this? I think I want to just skip over the code. I just want to know what to do and then do that. Like, I kind of do know what to do already, right? It's like, you want to take the gradient of... No, I don't know how to do it. I need a bit more help before I can start implementing stuff. I'm skipping this. The training data is the list of tuples x, y, representing the training inputs and corresponding desired outputs. The variables epoch and mini batch size are what you'd expect. The number of epochs to train for and the size of the mini batches to use when sampling. Okay, so I'm guessing we've got def stochastic gradient descent on self, which is going to use training data, which has a really complicated type. So I'm going to skip typing it for now. Epoch is an integer. Mini batch size is an integer. And eta is a learning rate. If the optional argument test data is supplied, okay. Training data, test data. Then the program will evaluate the network after each epoch of training and print out partial progress. This is useful for tracking progress but slows things down substantially. The code works as follows. In each epoch, it starts by randomly shuffling the training data and then partitions it into mini batches of the appropriate size. Okay. In each epoch, so for blank in epochs. Randomly shuffling the training data, so import random, right? Random dot sample shuffle. There we go. Random dot shuffle the training data. So training data. Does this return itself, or like does it make a copy or not? Let's check. Python import random a equals 1 2 3 4 a random dot shuffle a. Okay, so it doesn't return a copy. Randomly shuffle the training data, then partition it into mini batches of the appropriate size. So for, okay, so len of, no, we know the mini batch size. So mini batch size over length of training data is how many batches we're going to have. So for I in this, mini batch equals training data from I to I plus, or this I is I times mini batch size. What am I doing here? Range this. And do an integer division. Up to I times mini batch, I plus 1 times mini batch size. Yeah. I don't like how hard this part is to read, so I'm going to rewrite this as while I is less than len of training data, I plus equals mini batch size. I starts at 0, and then mini batch is a slice of training data from I to I plus mini batch size. It's a little easier to read, I think. Okay. This is an easy way of sampling randomly from the training data. Then, for each mini batch, we apply a single step of gradient descent. This is done by the code self.update minibatch eta. Okay. Update minibatch eta. Oh, this needs to be range of epochs. Which updates the network weights and biases according to a single iteration of gradient descent using just the training data in minibatch. Here's the code for the update minibatch method. Well, I don't want to read that. So I'm going to skip over it. Most of this work is done by delta nabla b delta nabla w equals self.backprop xy. This invokes something called the backpropagation algorithm, which is a fast way of computing the gradient of the cost function. So update minibatch works by simply computing these gradients for every training example in the minibatch, and then updating self.weights and self.biases appropriately. Okay. Computing these gradients for every training example. Okay, so def update mini batch. It takes a mini batch, which has a complicated type. It takes an eta, which is a float. And I don't think it returns anything. Just like I don't think this returns anything. So update mini batch. If we take, we know that it's gonna. So is nabla what I was calling like del? Nabla symbol. It is. So this is the gradient of B. No, delta nabla B, delta nabla W. Wait, delta. Or what am I doing? Delta symbol. Okay, I guess I'm not sure what these B's and W's are. A fast way of computing the gradient of the cost function. So update mini batch works by simply computing these gradients for every training example in the mini batch and then updating self.weights and self.biases appropriately. I'm not going to show the code for self.backprop right now. We'll study how backpropagation works in the next chapter, including the code for self.backprop. For now, just assume that it behaves as claimed, returning the appropriate gradient for the cost associated to the training example X. So backprop returns the gradient of the cost function with respect to the B's and the W's. I'm not sure what X, Y are. I think we have to look at the code for update mini batch. Update the network's weights and biases by applying gradient descent using backpropagation to a single mini batch. The mini batch is a list of tuples X, Y, and eta is the learning rate. Okay, so we're actually going to change our weights and biases by this formula that we saw before, eta over m times NW. What's NW? Oh, for W and W in zip the weights and the gradient of the weights. NW is nabla W. Okay. Okay, so instead of looking at that, let's go look at the equation all the way up here, this. So, self.weights of I is equal to, what's the problem with this? Self.weights of I is going to be equal to what it was before, minus eta over m times how do I read this? This is the sum over j of the gradient of cxj with respect to this weight. So this is times sum of gradients of W, right? And then similarly for biases, self.biases of I, biases grad of B. for blank in len of self.weights, or for I mean, in len of self.weights, you do this stuff. M is equal to the len of the size of the mini batch. Grad of W and B, I think is, and this you have to do range around a number. Grad of W and grad of B, I'm guessing I take the I thing out of this, and that the grad of W and B is what you get from back prop mini batch. So let's see how close we are. So you had to call backprop more than once. Backprop, you call it on a single example, it looks like. Grad of W equals, we'll start it at 0 like they're doing. Zeros of W dot shape. For W in self.weights. And then you need to do a for loop just to do all the back propagations. So for xy in mini batch. So for each example, x is a number or is a image, and y is a label, as in it's a number. It's a number between 0 and 9. So delta grad W equals and delta grad B. It's always doing biases first. I'm gonna always do weights first, because I always think of it as weights and biases. Self.backprop of x and y. So x and y is a thing you do with a single example. Then grad of B, they're saying is I guess there's a contribution. How do I say this? Grad or delta grad of B has a value for every layer in the network. So it's not a single vector. And for this one, it's not a single matrix. It's a list of matrices. And every time you do the backprop, you get a list of matrices back. And then you want to sum them all together. So I don't know why they're doing this zipping stuff. I guess I do know why they're doing the zipping stuff, but I'm not going to. I'm going to do for I in range len of self.weights. Actually, I already did this. It's this. and I already called it the right stuff. So this is my version of it. Although I'm doing some of grad of W here. In this version, it's not a sum because I'm doing it inside the loop. And then instead of doing weights equals weights minus, I'm just going to do minus equals. It doesn't like np.zeros. Oh, because it's spelled differently. Okay. Most of the work is done by the self.backprop. This invokes... oh yeah, we already read this. We'll study how backpropagation works in the next chapter, including the code for self.backprop. For now, just assume it behaves as claimed, returning the appropriate gradient for the cost associated to the training example X. Let's look at the full program, including the documentation strings, which I omitted above. Apart from self.backprop, the program is self-explanatory. All the heavy lifting is done in self.stochastic gradient descent and the self.update mini batch, which we've already discussed. The self.backprop method makes use of a few extra functions to help in computing the gradient, namely sigmoid prime, which computes the derivative of the sigmoid function, and self.cost derivative, which I won't describe here. You can get the gist of these, and perhaps the details, just by looking at the code and documentation strings. We'll look at them in detail in the next chapter. Note that while the program appears lengthy, much of the code is documentation strings intended to make the code easy to understand. In fact, the program contains just 74 lines of non-whitespace, non-commented code. All the code may be found on GitHub here. Okay, so initializing the network. Feed forward, we called that apply. SGD. We called it SGD. I'm gonna actually call it train. They're doing the random shuffle just like we are. Okay, we didn't do this thing of printing stuff as we go, but that's okay. We can add that once we're actually running it. Then we update mini batch. They're also doing the slicing. Update mini batch. Update mini batch is what we just went over. We had to read how they're doing it to understand a little bit. Backprop, they did not even explain. I'm going to skip over it. Evaluate returns the number of test inputs for which the neural network outputs the correct result. Okay, so you just say argmax, which means give me the value in the vector that is the biggest, and then we're just gonna compare that to y. So yeah, if the biggest one is equal to y, that means it's right. Cost derivative, return the vector of partial derivatives cx over partial a. Or wait, derivative of cx with respect to a for the output activations. And that's just a subtraction. I think hopefully they'll explain why that would be the case later. How well does the program recognize handwritten digits? Well, let's start by loading the MNIST data. I'll do this by using a little helper program, mnistloader.py, to be described below. We execute the following commands in a Python shell. Import MNIST loader, get the data. Of course, this could also be done in a separate Python program, but if you're following along, it's probably easiest to do in a Python shell. After loading the MNIST data, we'll set up a network with 30 hidden neurons. We do this after importing the Python program listed above, which is named network. So I am missing def back prop, which takes a list of, or actually it's an ND array, np.nd array, so self, and it takes an example, and it takes a y, which is just an int. And it returns a whole bunch of stuff. It returns two ND arrays, actually. Tuple of np.nd array. And I'm going to pass because I don't know how to do it yet. So you make a network. Finally, we use stochastic gradient descent to learn from the MNIST training data over 30 epochs with a mini batch size of 10 and a learning rate eta of 3.0. Okay. I'm trying to find a good stopping point here. I think I'm gonna just stop right here before we start running the network. So we can't actually, like I can't actually run this yet because I haven't implemented backprop. So I guess next time I'll decide whether I want to just implement, if I want to just copy their backprop for now, or if I want to wait on running this until I've done it myself. Why is this actually being underlined? Cannot access update mini bat. Oh, I called this batch. Okay. All right, but that'll be it for now. Thank you for watching.